entropy is what we'll be talking about today. So far, we've talked about enthalpy, and basically, we know that if a reaction has a negative enthalpy, so it's exothermic, those reactions tend to happen more spontaneously than a reaction that has a positive delta H or is endothermic. Okay, but that is not always the case because there's another thing that comes into play when we're talking about is the reaction going to happen or not. Okay, now a lot of times when we talk about is the reaction going to happen or not, we use the word spontaneous. Is the reaction spontaneous or not? Okay, if it is spontaneous, then we say yes, the reaction is going to happen all by itself without any outside intervention. If it's not, then it won't. Okay, now the way that the AP people, instead of saying spontaneous, they used to say spontaneous, but now they say this: thermodynamically favorable. So if a reaction is thermodynamically favorable, which you're going to see that term quite a bit here coming up, then that means that yes, the reaction will happen without any outside intervention. Okay, if it's not thermodynamically favorable, then it won't. Okay, and enthalpy absolutely plays a part in that, but there's one other thing that also plays a part in it, and that is what's called entropy. Okay, entropy, which is not enthalpy, entropy is a measure of how disordered something is. So the degree of disorder is called entropy, and delta S is the symbol that we use. When something is becoming more disordered, okay, that is a positive delta S. So positive delta S is more disordered, and we'll talk about what that means here in just a second. And then a negative delta S means it's becoming more ordered. Okay? Now, everything has some disorder associated with it. Okay? Unless you are at absolute zero, which is 0 Kelvin. If you're at 0 Kelvin, then nothing is moving. There's no rotation. There's no vibration. There's no nothing. And that's the only time you'll ever have an entropy of 0. Okay? That's when things are completely organized or completely ordered, is when you're at absolute 0. Other than that, everything always has some amount of disorder to it because there's some type of motion in it. Now, how do you know when one thing is more entropic, you could say, than another? Okay, first of all, gases have way more disorder than liquids or solids do. Solids have the most order, and then liquids are less ordered, and then gases are way more disordered than the other two. Okay, so this has a more positive delta S. This would have, again, the change in the entropy would be much smaller for a solid. If you have more particles versus less particles, there's more disorder there. Again, that leads to a more positive delta S. Okay, if you have a large volume versus a small volume, the molecules can move around more. That means you're going to have a larger entropy, a more positive delta S. Okay, and then things at a higher temperature have more energy. If they have more energy, they have more entropy than things at a lower temperature. Okay, let's look at some examples here. Okay, example 1. Predict the sign, positive, negative, or 0 of delta S in the following reactions. So notice that in part A, you're going from a solid and a liquid to just a solid. There's two different ways you could look at this. You could look at it and go, well, we're going from 2 particles to 1. That's more ordered. And you're also going from a solid and a liquid to just a solid. Liquids are way more, not way more, but they have more entropy than solids do. So this is definitely a negative entropy. Okay, in letter B, you're going from a solid to a solid and a gas. Anytime you go from a solid and a liquid to at least one or more gases, that's always going to be a large increase in the entropy, so that would be a positive delta S. This is a negative delta S. Okay, letter C, notice they're all gases, so now really what we're doing is we're just counting the number of gas particles. There are 6 gas particles on the left, and there are 7 on the right. So more particles means more disorder. That's a positive delta S. Okay, on letter D, you're going from, now be careful here because notice that's a liquid. Okay, so the liquid part, kind of forget about that. You're going from 15 gas particles to 8 gas particles. Okay, and so that is becoming more ordered. That is a negative delta S. Okay, on letter E, you're going from 3 gas particles to 1. That again is a negative delta S. That's becoming more ordered. Letter F, you're going from from 1 gas to 2 gases. So that's a positive delta S. Letter G, be careful with those liquids there again. Again, whenever there's gases involved, you can kind of forget about everything else because gases are the ones that have the most entropy. And so you're going from 5 gas particles to 4 gas particles. So that is a negative delta S. And then the last one, letter H, notice that they're all gases and you're going from 2 gases to 2 gases. So in that case, the amount of disorder would be the same on both sides. So you would say that that is a 0 change in the entropy. 2 particles on both sides and they're both gases. So that would be a 0 in terms of the change of the entropy. Okay, example 2. Which of the following has the greater entropy, a metal at 273 or the same metal at 400? Again, at a higher temperature, you've got more kinetic energy. Remember, that's the number one thing that affects kinetic energy is temperature. So more kinetic energy, more disorder. So which one has the greater entropy? Absolutely the one at 400. Okay, letter B, a flexible soft metal like lead or diamond or a rigid network covalent solid. Again, if it's a soft metal, it means it can move around more. Again, it's all about disorder. Okay, so lead absolutely is going to have more disorder than the rigid network covalent solid like diamond. Okay, and then part C, 2 samples with the same mass of the same gas at the same temperature, but one with a pressure of 1 atmosphere and one with a pressure of 0.5 atmospheres. So you have the same mass, which means you have the same number of moles, and you have the same temperature, so PV equals nRT. Let's think about this for a little bit. Okay, if the masses are the same, the moles are the same. If R is always the same, and the same temperature, means that whichever one has the greater the greater the pressure means the smaller the volume. Okay, and so if the pressure is greater in one, that volume is smaller. So the smaller the pressure, the greater the volume. And remember, that was one of our things up here. Gases with a large volume have more entropy than gases with a small volume. So the one at the lower pressure is therefore going to have the greater volume, and the greater volume is going to have more entropy. Okay, now just like with enthalpy, where we did the enthalpy of formation of the products minus the enthalpy of formation of the reactants, you can do a very similar equation using the absolute entropies. Notice again, it's products minus reactants. But remember with enthalpies of formation, when something was in its elemental form, it had an enthalpy of formation of 0. Okay, that is not the case with entropy. Okay, and that's because, remember, unless you're at 0 Kelvin, everything has some disorder associated with it. So like nitrogen and hydrogen are both in their elemental form, but notice that nitrogen and hydrogen both have an entropy associated with them. However, you solve the problem the same way. When we calculate the entropy change, we're going to take the entropy of NH3 and double it. So the delta S for the reaction is going to equal 2 times 193, and that's our reactants, or our products, minus our reactants. Nitrogen is 192 plus, and then hydrogen's 131, and there's 3 of them, so 3 times 131. So 2 times 193 minus, and then in parentheses, I'm going to go 192 plus 3 times 131 equals, I think that's right, 2 times 193 is 386 minus 192 Yes, so I get an entropy for that reaction of negative 199. And notice that is in joules. That's going to come back to haunt us here in a little bit, but not yet. Okay, we'll talk about units once we get to our next lesson. Okay, now, would you predict that? Would you predict the entropy change to be negative? Absolutely, yes, you would, because you're going from 4 gas particles to 2 gas particles. That is becoming more ordered, and so absolutely, yes, you would predict without even doing that. So does your answer make sense? And yes, in terms of disorder, absolutely, yes. A negative value when you're going from 4 gas particles to 2 gas particles is 100% yes on that.